Unigine's global terrain is a virtually limitless terrain representing a certain fragment of Earth's surface. Terrain is likely to be the main object of your outdoor worlds. It defines environment, and therefore the impression your project makes, be it a game or a simulation software. Unigine Editor offers you the landscape tool to create terrains, be it an arbitrary landscape for a game or a georeferenced one to reconstruct an exact location for simulators, available for engineering and Sim SDK editions. In this tutorial, you will learn the basics of georeferenced terrain generation and get some basic instructions on performance optimization. This tutorial has a basic level and is mainly intended for developers of simulation software that requires a georeferenced terrain and having it handle all necessary data sources with the density providing the required level of detail. More detailed information on synthetic terrain generation, as well as other aspects of terrain generation and optimization, is to be provided in other dedicated tutorials. The interface of the landscape tool includes the preview panel with the world map and rectangular play area. It shows actual geographic borders of an area where your georeferenced terrain will be located. There is also the settings panel, the parameters panel. It works the same way as the parameters window of the Unigine editor, the generate button, and the sources panel, where you should specify the data sources for your terrain. Basic height, elevation, and albedo imagery, as well as masks, land cover, and vector data sources for generation of details, vegetation, roads, buildings, etc. The data for a georeferenced terrain can be obtained from OpenStreetMap or GIS software, such as Global Mapper. Please note that the quality of generated terrain is determined by the density of the data sources used. However, you can easily create high-resolution insets by adding a high-detailed landscape layer over a low-detailed one. This can be useful for flight simulators, where high details are required only for areas around airports. Procedural data refinement using Houdini digital assets is also supported. It can be used to improve the quality of generated terrain and will be covered in our advanced level series of tutorials. To specify the elevation data, right-click on the corresponding data type in the Sources panel. Choose Add New. Then select Georeferenced Mode and add georeferenced image files from the Elevation folder of the Tutorial Content add-on. Then click OK and wait for the data to load. Perform the same steps for the imagery data. As each data source is a georeferenced one, its borders are displayed in the corresponding area of the world map on the preview panel. Use the Focus option to find it. You can use Place Play Area Here option to define the location and size of your terrain. Take note that any data beyond the borders of the play area will be ignored. You can set play area size via the Parameters panel after selecting the corresponding settings selection. Let's adjust the size to cover all imported data sources. Unigine provides both georeferenced as well as synthetic terrain generation using ordinary raster images with no geospatial data that can be created in any image editor, but this is a subject of another tutorial. Via the Mode section, we can select the type of terrain we're going to create. We choose Georeferenced here. By default, the data source's processing order is determined by their density from high to low, but you can change ordering if necessary via the Processing Priority section. You can also speed up generation process using the power of your computer network by adjusting settings of the Distributed Computing section. Before we start generation process, we should specify the output directory location for our terrain, as well as the location to store generation cache. These settings are available via the Output File Location section. Let's create a landscape folder to store our terrain. Then we should specify the location for data cache, for example, on your local or shared storage if you use distributed computing. It is recommended to put cache files on an SSD storage device for best generation performance. You can manage the levels of detail for height, albedo, and masks data sources via the Parameters panel. These settings are generated automatically and can be adjusted to fit your project requirements. All generation settings that you make for your terrain can be saved to a landscape asset to be loaded and used later. You can do that via the File menu. Having set all the parameters, you can generate the terrain by clicking Generate. In the Generation Steps window that appears, you can select what is to be generated. It is very convenient, as you can save time, for example, when adding roads or buildings to your generated terrain without rebuilding the terrain itself. Let's generate the terrain using elevation and imagery data first. Use Curve Flag if you want your terrain to be curved. We're going to leave it flat. Enabling the Imagery Previews option will show previews for generated terrain on the world map. Click OK to start generation. Note the generation process may take a lot of time depending on the play area size and density of the data sources used. Upon completion of the generation process, you will be offered to optimize world settings for your terrain. We choose Apply. A new global terrain has just been created. It has the size of 10 by 10 kilometers in the virtual world. You can edit any height, albedo, or mask LOD of the global terrain object using the Terrain Editor tool. To start editing the current terrain, click the Edit button at the top of the Terrain Global tab of the Parameters window. If we choose the Height Edit mode and specify the brush parameters, we can adjust the terrain heights manually with the Alt plus left mouse button. Don't forget to click Apply when all adjustments are made. Remember that your changes made to elevation, imagery, or details will be discarded if you choose to regenerate these data layers. At this time, we just select Elevation. Well, you see the initial geometry has been restored. Now let's add some details and vegetation to our terrain. For this purpose, we should add some land cover data sources. They can be found in the corresponding folder of the Content add-on. Multi-selection editing is supported for the data sources of the same type, so select all the land cover sources and set up all of them simultaneously. First, let's add tags for forest, grass, and detail areas. Tags represent a color range, or an attribute value, range of values, and are used to filter the data necessary for generation of certain land cover areas or objects of the cultural layer, roads, buildings, etc. For each tag, we can specify a set of attribute filters to select certain data from the land cover data source. Several filters are used together with OR binary operation. After adding and setting up tags for data sources, we can specify generation parameters for the corresponding layer. So we select Masks, Land Cover, and via the Parameters tab, we do the following. Select all tags that we plan to use as masks for our terrain in the Masks section. In the Vegetation section, we can add a basic object for generation by clicking Add button and specifying object's name. This one is for forest. For our basic object, we specify the tag to be used for object placement on the terrain and the path to the corresponding node file that will actually be used to represent our object. We use Pine node. We can add as many objects as necessary, so let's add another one for grass and select the grass tag and the grass node file for it. This time we will generate only details in the land cover objects, so we select corresponding options in the Generation Steps window. Well, the objects for forest and grass has been created using the nodes that we specified. As you can see, our terrain looks a bit flat. We can now improve its visual appearance by adding details to it. For this purpose, we will use masks that we've just created. Click the plus button to add a new detail. By default, it is painted white and covers all the terrain. Select the mask to be used for the detail. Areas for details can be specified either by selecting a mask from the ones generated or simply using the albedo color of the imagery layer via the Mask by Albedo option. Here we can adjust threshold, width, and contrast to fit our needs. Drop the alpha channel to 0 to stop masking albedo. In the Textures section, you can specify desired textures for detail. As you're done with that, click Update Arrays to see the result. Don't forget to do it after making any changes to textures. Let's fix tiling in the corresponding section by increasing the size parameter. You can change the blending mode to overlap to hide underlying layers. We can set visibility distances for each detail to provide best balance between look and performance. It is recommended to configure distances so that fine details are displayed only at close distances, as they're unnecessary when they're far away. Also, each of the detail textures has the opacity parameter for fine-tuning. You can add as many details as you need, as well as manage their hierarchy. The subdetail flag indicates that the detail will use the mask of its parent. To edit detail masks with a brush, open the terrain editor in the mask edit mode. Choose the desired mask and level of detail. Specify the intensity and draw with the Alt key and left mouse button. Now let's add a cultural layer to our terrain, and we'll start with roads. Roads and buildings are generated on the basis of vector data, so we add a new vector data source, a shapefile with the whole road network for our area. Then we add a tag to filter the roads we need, selecting the ones having the highway attribute equal to primary. The same way we add the tag for secondary highways. As we added all necessary tags, we can proceed to setting generation parameters for the vector layer. To generate roads, we should add a spline object in the corresponding section. Let's call it Roads 1. Here we should select the tag, which filters splines from the data source, and node file to be placed along these splines. The type parameter lets you choose the type of objects to be generated for roads: static mesh geometry, decals projected on the ground, or both. You can choose which fits your project best. Decals may be enough for flight simulators, while a truck simulator would require geometry for roads. Choosing the appropriate type of objects can improve overall performance. The Split Segments option enables you to control the number of objects to be generated. The option adds more flexibility to tuning visibility distances for different parts of the road network separately. You can adjust heights and masks of the generated terrain to fit generated roads via the corresponding option when necessary. In this case, height and mask data of the global terrain will be modified in the areas along the splines, having the width specified by the area width. Remember that enabling this option significantly increases generation time. Let's create an object for secondary roads the same way. Now we can generate roads by clicking Generate and selecting the Vector Objects option in the Steps window. After the generation, 2 nodes with static meshes have been added for each road type. Houses, landmarks, and other such objects are placed at certain points of the terrain. Thus, we can add another vector data source named Unique Buildings, containing points, and use them as locations to place GSM towers. Then we specify a tag for them, set filters, and add a new point object in the corresponding section of the parameters panel for the vector layer. Let's call it a unique building. Then we select the tag that we just added and a node file with the GSM tower to be placed. Now you see a bunch of GSM towers were added to our scene. Another useful feature that contributes to recreation of the cultural level of the landscape is procedural generation of 2.5D buildings based on shapes, floor, and building category data stored in the vector data sources. Let's take a look at it. First, we add a new vector data source, Buildings, containing the data on our buildings and, as usual, specify tags. Building generation requires 3 tags: building shape, floor number, and building category, which defines text string type. We'll use a single category for all buildings by selecting the Buildings tag. You can add building categories by clicking Add and specifying a value of the selected tag. We set Yes, and then choosing a group of materials to be used for this category. Default option in the table specifies if this material is to be used by default for the rest of the categories, not specified in this table. Unigine provides a set of built-in materials inherited from the mesh base for generated buildings. This set of materials can be extended using your custom textures to add diversity to your virtual city. For more information on procedural buildings generation parameters, please refer to our online documentation. So we click Generate and select Vector Objects option in the Steps window. Now we have procedurally generated buildings, bringing the look of our scene to a new level. We've added a lot of features to the terrain to make it look more realistic, but without proper optimization, they may significantly affect performance, especially if the terrain is large. Now let us consider some basic optimization techniques that can be used to improve performance. More detailed information on terrain optimization is a subject of another tutorial. There are 2 aspects in optimizing content generated by the landscape tool: optimization of the global terrain itself and optimization of generated objects. Here are a few basic recommendations for objects. Properly adjust visibility and fade distances to avoid rendering objects when they are far away from the camera. Adjust density parameter for grass and clutters to acceptable level, as high density will significantly affect performance. Here we also adjust LOD settings such as visibility and fade. Where possible, mix geometry levels of detail with imposter objects, imitating geometry with a set of sprites. Choose the types of objects generated for roads according to your project's requirements. Use only decals where geometry is not required. As for the global terrain object itself, the key point here is to properly adjust the number of LODs and their densities, as well as to set their visibility distances. You can enable wireframe rendering to see the grid. When setting up LODs, you should avoid having too dense grid in the areas far away from the camera. Checking collisions and intersections against the most detailed LOD or a large number of LODs significantly drops performance. It is recommended to turn off the intersectable and collidable flags for all height LODs except the one with some middle density value to avoid extra calculations where possible. In addition to these settings, you can also gain some performance by adjusting options and parameters of the terrain global base material. Here you can enable Visualizer to see LODs of your terrain. If your terrain does not require insets, you can disable the Use Insets option to gain performance. On the Parameters tab, you will find Back Face Culling parameter that allows you to cut down the number of polygons by removing back faces, padding parameters, as well as the Subpixel Polygons Reduction parameter, which controls the number of too small tessellated polygons that'll be removed. Remember that a landscape indoor scene with all its features is a very complex element that significantly affects performance and requires optimizations to fit your project's requirements. For more information, please refer to our online documentation.